Hello, my name is Internacional Ramírez Guevara, and I have come to present my thesis that I did back in Colombia in coordination with Hernan, which is a professor back here at the USP. To begin with, let's recall a study that the ICAO published in 2016 that in order to reduce the emissions coming from the aviation sector in 2050 and to achieve those goals of net zero carbon, it's necessary to switch to sustainable aviation fuels and technology in mainly. Operations and infrastructure can also help, but they identified that technology and sustainable aviation fuel will be the best. For this, NASA addressed this problem using an improvement of the technology with the implementation of electric motors that were distributed along the leading edge of the wing in order to improve the airflow and thus improve lift at mainly takeoff and descent stages. The problem was that they didn't prove it. Basically, they enforced the distribution, a constant induced distribution of the induced velocity for the propeller, and they based this on works that were made almost 20 years ago. So what we need to do is to optimize the propeller in order to take into account its influence onto the wing and maximize its aerodynamic efficiency and propulsive efficiency. This is what the objective of this work aimed to do. Basically, optimize the performance of the whole aircraft, taking into account the propeller, using low fidelity methods that could leverage and accelerate the early stage of the design of an aircraft. This work used the blade element momentum theory. It consists of modeling the propeller as an actuator disk, and it was run through an optimizer several hundreds of times and iterations in order to find an optimal distribution for the twist and chord for the blades. The main contribution and main finding of this work was that it was able to beat the constant induced velocity propeller present at the X-57 at mainly high velocities, and it adapted to the several different conditions. And also that it was able to outclass and outperform the constant induced velocity propeller at different positions of the propeller with respect to the leading edge of the wing. Here we can see the plot that the CLB parameter is basically the difference of the blown and unblown wing with both propellers, and when done the subtraction of both efficiencies, it can be seen that the optimal propeller outclasses the constant induced propeller at all positions. For this study, I've used CFD simulations with a vector disk approaches that show that the best possible approach for this one, for this study, was mainly located along the leading edge. Those are the references that I've used in my work. Well, some of them, just that I presented here. And thank you so much for your time.